Okay, thank you for your introduction. My name is Hong Kim. I'm a PhD candidate at Yonsei University. My presentation today is about detection of construction equipment using deep convolutional networks. I'd like to start by discussing research background. Computer vision technology has attracted much attention recently because it can provide some visual data, such as which objects exist and where they are and when they appear in images. So using these kinds of data, we can generate some managerial information such as progress, productivity, and quality and safety. So visual sensing using computer vision technology includes the four major tasks. What I want to focus today is a detection task, which can generate the object types and the location and the time they appear in images. So using those data, we can produce some context information and managerial information. The figure shows one of my previous studies, and in this study, the individual safety levels are automatically assessed using an object detector and fuzzy inference system. Some typical characteristics of construction site images cause difficulties in detecting construction objects. So the construction site is conducted in an unique outdoor environment, and there are a lot of participants and equipment and materials are involved in construction, and there are appearance changes and illumination variations are severe too. So the detection model is hard to maintain the object detection performance in construction site images. So I'd like to introduce a few studies in the construction industry. Two studies use histograms of gradient features to detect dump trucks and hard hat of workers. And the Kim et al. Presented a scene parsing method for understanding the whole area in images. And the Dimitrov and Gorpard classified construction materials using an edge filter bank and polar space features. The major limitations of the conventional detection models are summarized in three factors. The first, the models use hand-engineered features. The hand-engineered features require a considerable optimization process and the domain expertise. And in general, conventional model has insufficient detection performance. And third, the model has a limited generalization capability. In other words, even when the test data is slightly different from the training data, the detection performance can be very worst. Sorry for my English. So what I want to address this issue is using some very recent technique, deep learning method. But challenges to implement this method is first, hardware and efficient algorithm is required, and big image data also required. But the researchers in computer vision communities overcome these barriers recently, so the performance of the detection model or other kinds of visual tasks is very high nowadays. But in construction communities, the problem is the image data, amount of image data. So we do not have a lot of image data available in this area. So we address this issue using some technique to train the deep model. So train the deep models for detecting construction heavy equipment with a limited amount of data, we used a transfer learning method. So from now on, I will explain the proposed model. So this is the model used in this study, which is called region-based fully convolutional network. In RFCN, it's called RFCN. And RFCN extracts the visual features in convolutional layers and estimates the candidate regions in which a target object is likely to exist, and determines whether a target object exists in each candidate region through position-sensitive score maps and pooling layer. This slide illustrates convolutional operations. The convolutional operation is an element-wise multiplications using a convolutional filter. The convolutional operation is performed on a pixel of input image, and which yields a single output value. And a feature map consists of a convolutional output values corresponding to the convolutional filter. And this slide shows the max pooling operation, which was used in our model after the first convolutional layer. So the max pooling operation selects the maximum value in the area covered by pooling window. So the figure shows the residual learning, a building block of residual learning and each formulation. In RFCN, in convolutional layers in RFCN, this building block is these building blocks are used to increase the depth of the networks. Using this residual learning framework, we have two major effects. The first, we can use the original input data information even when the layer is deeper. As you can see in the figure, input is added without any modification through a short connection. Maybe you can see this flow before the last activation. And second effect is, in the training process, it helps determine the proper representation of the networks by directing the way of updating process. So let me review the proposed architecture again. So in RFCN, the convolutional layer extracts the visual features, and then region proposer networks produces candidate regions, and then position-sensitive score maps and pooling layer determines whether there is a target object or not. So this slide shows the region proposer network pipeline. And from the feature maps, the new feature maps are generated by using a convolutional filter, 3x3 filters. And at each location of a new feature maps, 9 anchor boxes are created, and it is determined whether there is an object or not through a softmax classifier, and the coordinates of the box are adjusted from the smooth element loss function. This slide illustrates the position-sensitive score maps and its pooling layer. The upper flow determines the class of the target objects, and the bottom flow determines the coordinates of the bounding box. To train such a complex model with a limited amount of training data, we have to use some technique called transfer learning. Transfer learning is a method for utilizing sufficient knowledge from the source domain with a lot of data to perform a specific task in a target domain with a small amount of data. Using this method, we can train the deep model very efficiently and effectively. Okay, I will explain the experimental results and discussion. And these are experimental settings. You can refer to my paper more details. And to evaluate the generalization performance of the proposed model, we create the AIM dataset from AIM dataset, which has 5 construction equipment class. The images are collected from ImageNet, labeled by our research group. And this graph shows the pose statistics of the AIM dataset. Among the 17 poses, the 8 poses are dominant, which includes the frontal, left, right side. These are evaluation criteria. So to evaluate the proposed model for construction equipment detection, we set 3 experimental conditions. The first, we trained the model with only AIM dataset. The results is shown in the second column, and we trained the model with using transfer learning. And the last experimental condition is using transfer learning, and plus we add some online hard example mining technique. And online hard example mining technique is that the method only selects those candidate regions with high loss in the training process to enhance the performance of the model. As you can see in the table, without transfer learning, the model was not trained at all. And with transfer learning, we can train the model very effectively. Average time taken to train the model is about an hour per 10,000 iterations. So average time taken to process a single image is about 0.07 seconds, which means that 14 frames per second can be processed. And table shows the average precision for each class. And these are precision recall curve per class. And the table shows you precision recall value with a specified detection threshold. So, as you can see, the detection performance of the proposed detection model is very high. And these are the detection results per class. And these are also the results at a large scale. The model are very robust enough against the occlusion, noise, and illumination changes. So the models sometimes fail to detect the object correctly. Sometimes the model misclassified the taxi as a road or roller and merged the bounding box or missed some objects. So the performance of the model used in this study is really high, very high compared to the original RFCM model. So reason for the high performance are first, most objects exist near the center in the AIM dataset. And second, in general, the construction equipment has an eye-catching bright color, which helps the detection of the model. And third, the AIM dataset, only 8 poses are dominant in the dataset, so it helps increasing the detection accuracy. The reasons for the failure cases are 2. The first, lack of poses of construction objects. In test data, if the object in the test data showing on top size then the model failed to detect the object correctly, because in training data set, the only frontal or left or right side are included. So, and second, when an object in test data is too small, the model failed to detect an object. So let me conclude my presentation. So this is the very first study using some deep learning method for detecting construction equipment. So the method showing the way to train a deep model with a insufficient amount of data using transfer learning method. The feasibility of convolutional networks is verified. And the generalization capability of the model was really high. So for a future study, the image data should be increased to include some more poses and more construction object classes. To do that, efficient image data collection methods should be developed. And we will conduct a future research to infer the context of construction operations from the data generated by this method. These are references. Thank you for listening.